Awesome. Thank you so much for joining me this afternoon, and thank you for giving me the opportunity to give this fast pitch in front of all of you. So today I wanted to talk about repurposing depleted oil fields for enhanced geothermal energy. And you're probably familiar with geothermal energy, which is heat from under the Earth's crust. And in order to extract this energy, we need three things: water, heat from hot rock, and permeable rock. Underground reservoirs of water are heated by the hot rock, which can then heat a working fluid, which turns a turbine, thereby producing electricity. The issue with geothermal energy is that we are limited geographically to where this heat can be extracted. With enhanced geothermal energy, we really only need heat from the hot rock. Water can be pumped down to where the hot rock is, and rock that's not permeable can be cracked in order to allow the water to flow through, to allow for heat exchange between this hot rock and the water. The challenge, though, is that we need to drill around 3 to 10 kilometers deep underground to get to this hot rock, which is deeper than we would for regular geothermal. And we also need a way to make the rock permeable by engineering cracks in it. Still, this method gives us a lot more flexibility when it comes to siting for enhanced geothermal energy. So we have extensive knowledge of drilling deep from the oil and gas industry. And even ARPA-E has funded projects into drilling deeper for geothermal energy. But these drilling operations still cost tens of millions of dollars. So if you take a look at an example, for a 25 megawatt enhanced geothermal plant, the exploration and drilling costs can be a significant fraction of the overall construction costs of such a plant. But if we use resources that already exist, we could actually slash these costs dramatically. Can we possibly get away with not drilling? So here's a map of the geothermal resources in the United States. And as you can see, these black dots that are predominantly in the western part of the United States represent sites in which geothermal energy can be extracted naturally. But even east of the Rockies, there are a plethora of favorable sites for enhanced geothermal energy, which are represented by the red and orange colors. And it's in these locations that there are hundreds of thousands of oil wells, ranging in depths from up to 10 kilometers deep. So we could actually use, many of these oil wells are abandoned, so we could use them to get to the hot rock that is deep under the ground. So if we look at an example, in the Anadarko Basin, there are thousands of oil wells, and many of them are up to 5 kilometers deep. Some are even up to 10 kilometers deep. One of the questions that we need to ask ourselves is, can we reuse the cement casing that lines these oil wells for pumping water for enhanced geothermal energy? We may also need to drill deeper to get to the hot rock that's below the surface. But the exploration cost would be significantly minimized given that we've already drilled pretty deep down. We can also take advantage of directional drilling that's known in the oil and gas industry in order to get to hot rock that might be a little harder to reach otherwise. So one of the challenges that I mentioned is that we need to be able to fracture this rock in order to allow for water to flow through and get heated up. So with oil wells, with oil wells that have already been drilled, we would already have some cracks near these oil wells in the surrounding rock. So we need to be able to measure where these cracks are and determine what this optimal fracture map would look like. We would still need more cracks in order to make a pathway from one well to another so water can flow from one well to another. And the way to do this is that we would inject high pressure water into one of these wells, which would allow more cracks to form or old cracks to propagate even more. So the way this works is that cold water is injected into one well. It gets heated up while it flows through the hot rock through these different tortuous pathways, and then the hot water is finally pumped out. Of another well. So it's really important that we're able to characterize the subsurface in order to understand where these cracks are and how they propagate. It's really important that we also understand how the water itself is flowing through these cracks, what pathways it's taking, and what the temperature of the water is throughout this process. So there are currently, here are a couple of methods that are currently being used. One is microseismic methods. So these methods allow us to figure out the rock structure, but it doesn't really tell us much about where the fluid is flowing. With magnetotelluric methods, we can actually measure fluid flow as a function of time, so over the operation of a plant. But these methods tend to be very noisy, and they may not work at the depths that we need for enhanced geothermal energy. So we could perhaps use both these methods in conjunction, but the point is that the technologies that exist today are still lacking in some form for developing enhanced geothermal systems. So what I'm trying to get at is that we're trying to engineer a heat exchanger deep under the ground. And what are some of the ways that we can do this? Well, we might get inspired by heat exchangers from industry in order to develop efficient known geometries for heat exchange deep underground. So perhaps we could develop methods that allow us to drill very precisely in the exact locations that we want, which again stresses the need for sensors that allow us to understand the subsurface a lot better. Right. So what determines what the optimal fracture system is? Well, the water that flows through these cracks needs to get heated up to a hot enough temperature, and yet we also don't want the rock itself to get cooled down by this water. We also don't want the water to escape from the system, because we want to be able to pump as much of the hot water as we can back up, so we can use most of the water. So this is a pretty tough balance to get right. But as if, developing these enhanced geothermal systems wasn't challenging enough, why don't we try jumping off into the deep end? So this is the Shell Perdido oil platform. It's located, it's about 3 kilometers above the ocean, below the ocean surface, and this is about half a kilometer deep into the oceanic crust. So we have the technology to drill deep below the ocean surface, and although the idea of offshore enhanced geothermal may seem ludicrous, there are actually some key advantages to this approach. So at the Shell Perdido oil platform, the water temperature at the bottom, near the surface of the ocean, is around 4 degrees Celsius, which means that we can actually extract a lot more energy from the water itself. The oceanic crust is also easier to fracture because it's mainly composed of basalt. The oceanic crust is also a lot thinner than the continental crust, which means that we don't actually have to drill as deep to get to the same or similar temperatures as we would on Earth. The challenge, of course, would be electricity production underwater and transporting that electricity to populated areas. But I'll leave that to the audience to think about. So in conclusion, I wanted to bring up the possibility of using known resources such as existing oil and gas wells for reliable and renewable enhanced geothermal energy production. Thank you all.